So my name is Thomas Helfer. I work at the French Atomic Commissions with my colleagues, which share the co-authorship of this presentation, of this talk, Clément Introïni, Raphaël Prat, and Tommaso Barani. So the main idea is to show you two open source applications that we have built in my lab on top of MFEM, which are dedicated to nuclear fuel modeling. So who are we? We develop a numerical platform called Pléiade. So we developed this numerical platform called Pléiade for modeling nuclear fuel behavior. This has been developed in 20 years in collaboration with industrial partners in France, EDF and Framatome. It's a platform which is mostly driven by question about quality assurance and verifications and validations with respect to our experimental database and material databases. To support the requirements of the safety studies in the nuclear world to help our industrial partners. One thing you must know is that the application that we built inside this platform have to describe a myriad of coupled nonlinear physical phenomena. And both in normal operating condition when the nuclear reactors was as expected in its daily life, but also in what we call off-normal operating conditions, where we try in experimental reactors to mimic what could happen during nuclear incidents. We have developed this platform since 20 years, mostly based on an in-house finite element solvers called custom. And this finite element solvers have soft roamings recording HPC performances. So this is the main driving force behind the development of the two applications that I will present. I will present the first one, and then Clément will present the second one. The first one is MFEM-MGIS, which I already discussed, I think, 4 years ago in a previous MFEM meeting. So I won't go into the details how we built this application. Everything is described on the website in the talk 4 years ago, and also in a recent paper in the Journal of Open Source Software. But basically, this application is dedicated to thermomechanical simulations coupled with damage. So what we'll see in a few minutes. And after my talk, after my part, I will give the talk to Clément Introïni, will describe SLOTH, which is an application dedicated to multiphysics coupled simulation, which includes heat transfer, phase changes, multicomponent diffusions, and thermodynamic equilibrium. So sorry. So MFEM-MGIS in a nutshell, basically the idea is to write a generic thermomechanical solver based on two libraries, MFEM for everything related to finite elements, linear solvers and nonlinear solvers, and two libraries that I wrote called MFront and MGIS that I will describe in a few minutes. But basically the idea is that everything related to the material knowledge that we will introduce inside the simulation are handled by MFront and through the MGIS API. I've shown 4 years ago that one of the goals was to describe a very high level API which is able to describe solver precondition and boundary conditions, focus on the physics so that engineers can use it directly without being, I would say, distracted by numerical details. So the main focus was to be able to describe multi-material models, small finite strand analysis, isotropic and autotropic material laws. Most of them were not available in MFEM at the time, so this is something that we added to MFEM in this library. So I've give you some references, the GitHub website and the repository, and also a link to the tutorials. So about MFront, which is what we added basically to MFEM, it's an open source code generation tool which is dedicated to describe your material knowledge. So it lets you implement some very simple things like the Young modulus as a function of temperature or the thermal conductivity, but it also enables you to write quite efficiently and simply complex mechanical behaviors, which can describe damage, plasticity, viscoplasticity at small and faint train, that kind of things. It's really driven by quality assurance requirements, and it's also used in many industrial nuclear fuel codes, such as Serrano and Galileo. And we try to focus on high performance, ease of use, and portability. MGIS, which is a project which allows to use MFront in many solvers, including MFEM, hence the name MFEM-MGIS of the application that I'm going to describe. So, as I said, I won't describe the application per se because I already did this 4 years ago, but mostly I will focus on some simulation that were performed with MFEM-MGIS. And the first one was a PhD work by David Siedel, where we implemented many phase field approach to brittle fracture and arbitrary phase field models inside MFEM-MGIS based on the minimization of this Lagrangian. And we leverage MFEM-MGIS to use this micromorphic approach to rupture to describe various kind of things and couple damage with viscoplasticity and finite strand analysis. The most important point regarding phase field approach to rupture is that the irreversibility constraint can be treated exactly at the integration points. And the fact that we are minimizing this energy, we have set up in FNGS a simple alternate minimization scheme where we first minimizes the Lagrangians, so the energy with respect to the displacement, and then we minimize this with respect to the damage. So the details are given in this conference paper, and mostly we leverage MFEM to see the effects of higher order finite elements. And here we have a test case where we reproduce a paper from Roberto Alisi about shear-driven fracture, where linear elements leads to really poor results, and things gets better as we get towards higher order elements, and it's something which is quite natural with the micromorphic approach and the MFEM abilities. And the second example, which is closer to our main concerns, is the brittle fractures of a fuel pellet during a reactor startup. So this is typically a fuel pellet. It's about 4 millimeter wide. The radius is about 4 millimeter. And during the reactor startup, we have a very strong temperature gradient inside these pellets. So the center is more hot than the outer parts. The temperature gradient is about 100 Kelvin per millimeter. And at the end, this creates elastic stresses inside the pellets, which are relieved by the creation of these crack networks that you can see here in red. This is the simulated ones. And this is the kind of simulation that we were able to do with MFEM-MGIS with about 20 millions of degrees of freedoms. And this shows the coupling between heat transfer analysis, micromorphic approach to damage, and mechanics. The simulation were run in our French supercomputer TGCC on about 2,000 MPI processes with good scalability. So at the end, you see this complex crack propagation. And also, we have to mention that the crack propagation is unstable and that you have to break the initial axisymmetrical mechanical field to localize the damage into those cracks, which is quite difficult to do. And we were quite happy by the alternate minimization algorithm that we have set up because we were able to describe this complex crack network, which appears quite in an unstable manner. So I will go a little bit further to another examples of what we are able to do. In this example, we describe representative element volume of neutral fluid, and this is done by my colleague Tommaso Barani. And we try to model what can happen during fuel annealing after irradiation. What happens during irradiation is that we create bubbles with pressurized gases. And if we anneal the fuel, pressure inside the bubbles increases, and then you have fragmentations of this RVE, which leads to release of fission gas products. So we have set up, in the context of an European project called Opera-HPC, a simulation of those effects, and we were able to describe the progressive rupture of the matrix with a very simple model and try to correlate that with the experimental data. And I'm sorry, it's a bit not quite readable, but you have the experimental data in blue, and at the very beginning of the annealing, we have a good correlation between the release of fission gas products, which comes from the cracking of the bubble, and the experimental data. So a good correlation between simulation and experimental data. Another example, just to show that we do a lot of periodic computation at the heavy level. It's a description of a specific nuclear fuel called mixed oxide fuel, which contains uranium and plutonium. And in this case, we just modeled a matrix and an inclusion, and we try to compare performances of and make some verifications of MFEM-MGIS against fast Fourier transforms, and also try to measure the performances of MFEM-MGIS on our clusters with good strong reliability, as shown on this figure. So this work on the solvers was mostly done by Raphael. Last thing that we wanted to mention, so MFEM-MGIS is now mostly focusing on post-processing, and we have developed a library to do things dedicated to mechanics. And for example, what we do in fine strain analysis is that we have this first pure Kirchhoff stress, which is very convenient for the developers of developers of thermomechanical solver, because everything is simple with this stress, but it's not quite meaningful for the user. So we have developed this post-processing, for example, a post-processing which is able to take the first pure Kirchhoff stress, transform it to the Cauchy stress, which is what the user expects, and that rotates it in the global frame in for autotropy behaviors. So we have introduced a lot of processing, which are quite interesting for most solvers. So this module is also solver agnostic. So if you ever have your own finite element solver, maybe you could be interested by those developments. For the transitions, I have some unsorted specific perspectives that I won't develop about what we want to do, because I have to let Clément talk. Clément, try to take the stream. I don't know if you can just... this time I would just say that no, MFEM-MGIS was developed 4 years ago, and we have to catch up with all the very nice developments that were made recently. And one of the biggest challenges that we will have to do is to port and to couple MFront and MFEM on GPUs. So now we have MFront also ported to GPUs, but we haven't linked them, MFEM and MFront on the GPUs. So this is something that we will have to do. Clément, I'll let you speak.
Hello, everyone. I'm Clément Introïni. I'm very happy to be here to present you SLOTH, the multiphase-field multicomponent framework we are developing in the Pléiades platform. So SLOTH is mainly based on phase field modeling. So I think it's interesting to fix ID in the two-phase case. So phase field modeling is based on the diffuse description of the interfaces between two materials, two states, two phases. So the interface is described as a transition layer of finite thickness, here denoted by epsilon on this picture. And with the phase field modeling, the variable here denoted by phi vary suddenly but continuously inside the interface. So with phase field modeling, we have an implicit tracking of the interfaces, and we have a continuous variation of the material properties. So there exists a lot of phase field models, but basically the two main models are the Cahn-Hilliard and the Allen-Cahn phase field models. On the left, you have the Cahn-Hilliard equation, and on the right, the Allen-Cahn equation. And basically, from a mathematical point of view, we have to keep in mind that Allen-Cahn is just a diffusion reaction equation, and the Cahn-Hilliard equation is a fourth-order parabolic equation, elliptic parabolic equation, because as you can see, we have a double Laplacian for the variable phi. So, and both Allen-Cahn and Cahn-Hilliard equation are highly nonlinear equation, because mainly we can have the kinetic parameters that depend on the variable, but we have also this term, this function, the double well potential. It is a nonlinear function that tend to separate the two phases. Cahn-Hilliard equation is used for conservative variable, and for conservative problems, we can mention, for example, spinodal decomposition, the evolution of bubble in a gas, etc., etc. And Allen-Cahn equation is used for phase when we have phase change, for example, melting and solidification. So in the Pléiades platform, we are interested in phase field modeling in order to study the nuclear fuel behavior at different scales of description, from nominal operating condition to severe accident condition. So as you can see on this picture, on these pictures, we are interested in highly coupled multiphysics problem in extreme condition in terms of temperature and composition. And these problems involve multi-phase, multi-component system. So we have developed SLOTH on top of MFEM in C++. It's a small code developed since 2023. It's open source, developed under LGBA license. So SLOTH provides the Cahn-Hilliard equation, the Allen-Cahn equation, but also the multi-component diffusion equation and heat transfer equation. And in order to perform the multiphysics simulation of interest for nuclear, our nuclear application, we have also a coupling between computational thermodynamics and SLOTH in order to perform CALPHAD informed phase field simulation. On this slide, I show you an overview of the SLOTH feature. So as I said, SLOTH is developed on top of MFEM. So we benefit from all the features coming from MFEM, namely the CPU parallelism. And on top of, based on these features, we have developed different packages in order to perform multiphysics simulation. So we have a packages dedicated to spatial discretization with the management of meshing of boundary conditions, such as the Dirichlet-Neumann periodic boundary condition. And we have only now uniform refinement. So the introduction of the development of adaptive mesh refinement is planned for the next months. We have also a package dedicated to the time discretization. We can use explicit, implicit schemes, and our problems can be solved by using either partitioned or a monolithic solution algorithm. So we can choose different kind of finite element, different solver, and we have also a package dedicated to post-processing. For post-processing, we use only ParaView because I'm more familiar with ParaView. So SLOTH provide also different services for performing multiphysics simulations, such as the management of the variables associated to the problems, and the variables associated to the other problems in the multiphysics coupling scheme. Services for the management of material properties and the calculation of some quantity of interest, for example, L2, L infinity errors, and interesting for phase field application, the evolution of the energy density. So we have also documentation. Actually, as I said, we have only MPI parallelism, but we plan in 2026 to work on GPU parallel computing. We plan also to add save restart features because our simulation are longer. So it's an interesting feature, and we plan to add high order time stepping method. On this slide, I show you a schematic overview of one time step doing by SLOTH.
You've got about one minute left in the presentation.
Oh, okay, very quickly. Sorry. Okay, I present this slide and I finish by illustration. Okay. On this slide, I show one time step performed by SLOTH. So we have two nested loops. The first one is the coupling, different coupling, and each coupling is composed of different problems. We have different type of problems that can be solved by partitioned or monolithic algorithm. And we have three type of problems: partitional differential equation, zero-G model. Actually, we have only CALPHAD computational thermodynamic models, and what I call the remainder. So the remainder is, for example, physical property computation, update variable, etc., etc. So, and for partial differential equation, our main MFEM dependencies is obviously time-dependent operator, and block nonlinear form integrator. So to conclude, I will show you this calculation. It's a very fresh result. It concerns the implementation of the Cahn-Hilliard equation, but not only the implementation of the Cahn-Hilliard equation, but because this development enables now us to have a monolithic solution algorithm for SLOTH problems. And recently, for this test case, three-dimensional test of two kissing bubbles, we have performed a performance test, and we observe at the beginning of the test a good scalability, but we have a break when we consider a lot of degree of freedom. So actually, we don't have the explanation. We assume it is a load balancing issue, but profiling and optimization is in progress. I have not, probably I have not enough time. It's a first promising multiphysics simulation we perform with all the feature provided by SLOTH. So, and you have an example of the multiphysics coupling scheme performed by SLOTH. Okay, very quickly, I'm sorry. SLOTH is a very recent phase field solver built on top of MFEM. The development team is small but dynamic. We have a lot of students, a lot of collaboration with my colleague at CEA and Polytechnics in France. If you want to collaborate, collaboration is welcome, so don't hesitate to contact us. So as I said, our future challenges is for MFEM-MGIS and SLOTH, the GPU parallel computation, adaptive mesh refinement, and we will also develop a coupling between MFEM-MGIS and SLOTH in order to provide, in order to be able to couple SLOTH with thermomechanics. We have one needs. We can discuss on Slack if you want about the solution algorithm. We use a method deprecated, so if you have an alternative or recommendation, it's welcome. And we have also a need for post-processing. So thank you for your attention. Thank you for your invitation. Sorry for this very quick talk.
All right. So first of all, thank you, Thomas and Clément, for calling in from Europe and for presenting this really interesting work. I wanted to ask about the post-processing that Thomas showed at the end. Do I understand correctly that this just works in memory where you can pipe operations on unstructured data? And
Yes.
is this sequence of operations implemented serially, or are some of those merged?
It's like an expression template in C++. So what we do is that we create what we call the evaluators of the values. So it's kind of a way of creating kernels that will be evaluated, and everything is all those operations are embarrassingly parallel because they are executed on each integration point independently. So this syntax is just a way to create the kernels that we want for the post-processings. And then we, at the end, you know, there is this SU at the end of the first examples. It's a way to save the results of these evaluations inside a new field. I don't know if I was clear, but basically it's a way to create, an easy way to create kernels dedicated to mechanical post-processings.
It's a nice syntax. Yeah, thank you. And please don't hesitate to reach out on Slack with the issues that you listed so we can follow up there. Thank you.